To practice the implicit function theorem, let us consider the following exercise. We have the equation e to x minus e to y minus x minus y is 0, and we have the point x0 is 0 and y0 is 0. Well, and the question again is whether this equation does define an implicit function y a function of x near this point. And if so, let's write the Taylor polynomial of order 2. So we denote the left-hand side as a function small capital F, e to x minus e to y minus x minus y. We see that this function is continuous and defined in entire arc 2. So this is C infinity R2. Then we evaluate the function at the point 0, 0, and we have 1, minus 1, minus 0, minus 0, which is indeed 0. That's good. That means this point lies on this curve. And we want the partial derivative with respect to y, which is 0, minus e to y, 0, minus 1. And the derivative at the point 0, 0 is equal to minus 1, which is minus 2. This is different from 0. And from these three results, that the function is continuous, the point does satisfy the equation, and the derivative with respect to y is non-zero. From these three results, we see that the implicit function y as a function of x exists. And let's find the first and second derivative of this function. Either we can differentiate this equation once with respect to x, looking at y as a dependent variable. So derivative of e to x is e to x, minus derivative of the exponential is e to y times y derivative, because this is a composite function, minus 1 minus y derivative is 0. And when we use the values for x and y, we can find the y derivative. Then we have e to 0, which is 1, minus y derivative, minus 1 minus y derivative is 0. And we have 1 minus 1 is 0, minus 2 y prime is 0. That means y prime at the point 0 is 0. Or we should write f prime at 0 is 0. Alternatively, we can compute f with respect to y, with respect to x, and we have e to x minus 0 minus 1. And then, so this is another alternative, another way how to compute the first derivative. F prime or y prime is minus f with respect to x divided by f with respect to y, which is e to x minus 1, minus fraction e to x minus 1, divided by minus e to y minus 1. This can be simplified a little to e to x minus 1 divided by e to y plus 1. And then when we use the values for x and y, we can find the derivative of f at 0 being 1 minus 1 divided by 1 plus 1, which is again 0 in the agreement with the previous result. Well, sorry, I sometimes use y prime, sometimes small f prime, this is the same. What about the second derivative? We can consider this equation and we can differentiate once again. So e to x divided by e to x derivative is e to x minus derivative of e to y is e to y times y derivative once again, plus e to y times y second, minus minus 1 gives 0, and minus y prime gives minus y second. And now when we use that x is 0, y is 0, and y derivative is 0, then we have 1 minus, this is 0, this is 1, so 1 minus y second is 0. So let me check this. Yeah. Y second is 1/2. 0. Or another approach is we can take the formula for f prime, which is here, and we can differentiate this once again with respect to x. So we have e to y plus 1 square, and the derivative of the numerator is e to x times the denominator e to y plus 1 minus e to x minus 1. And then it's not important what comes here, because when we evaluate this for x is 0, this will be 0, right? And well, for the sake of completeness, let's write this. E to y, the derivative is e to y times y derivative. Then the second derivative at 0 can be computed from this formula when we use x is 0, y is 0, and y derivative is 0. There is no minus here because we have reduce this minus against this minus already, right? So 1 plus 1 is 2, square is 4. And here we have 1 times 1 plus 1, which is 2, minus 0. So this is again 1/2. You see the same as before. Now, when we have the first and the second derivative, we can write the Taylor polynomial. The function value is 0 plus the derivative is 0 plus the second derivative is 1/2, and in Taylor we have 1/2 of the second derivative, so 1/4. Times x minus x0 square, so x square. So t2 is just x square divided by 4. So we can sketch the graph of the function, but not the entire graph, only a small piece of that. And x squared divided by 4 looks like that. The function value is 0, the derivative is 0, and the second derivative is positive. So we see this function small f has the local minimum at 0. Quite a useful result if you consider that we have not the formula for small f available. We have got the formula, and still we are absolutely sure that there is a local minimum. Using this machinery, there is no way to decide whether this minimum is local or global. It may happen that the values go down if you go away, and then it would be just a local minimum, not a global one. Or it may happen that the graph goes up, and this may be a global minimum. We don't know from this analysis. We can also practice the normal vector, which is the gradient of f. And this is fx at 0, which is 0, and fy at 0, which is minus 2. And the vector 0, minus 2 goes this way. We usually sketch a vector as an oriented arrow from origin. And in this case, we start at the point x0, y0, which happens to be origin in this case, but in the previous situation, it was out of the origin. So that was an illustration of the implicit function theorem.